Hello, everyone, and welcome back. In the previous video, we introduced Taylor and Maclaurin series. Now, as we go forward, we're just going to refer to these as Taylor series because we saw that Maclaurin series are really just Taylor series centered around 0 instead of any arbitrary value, say x equal to a. Now, the goal of today's lecture is to sort of formalize a lot of what we were talking about in the previous lecture. And in particular, we're going to talk about convergence of Taylor series. So we're going to start by introducing what's known as Taylor's theorem, which we'll see actually sort of generalizes the mean value theorem, which you probably remember from your intro calc classes. And then we're going to talk a lot about convergence. So when Taylor series converge. Now, we're pretty good at talking about convergence now because we have dealt with infinite series for quite a long time throughout the course of these videos. Right? We've talked about all kinds of different methods that we can use to determine when these things converge. And we also talked about this in the context of power series. So we're just going to put this in the language of Taylor series, although, a lot of what we're going to speak about has already been spoken about before. Okay, let's jump in. Let's start by recalling the mean value theorem. You might not remember this one off the top of your head, but it is one of the most important theorems in any sort of intro calculus class. And so basically it says that if you have two values of a function, f of b and f of a, the difference between those values is equal to the derivative evaluated at some point between them multiplied by the distance between these things, so sum c between a and b, right? So you might not remember this, but now you can kind of see it on the board. The only thing we're really assuming here is that f is differentiable. Now, what I also want to do is I want to rearrange this. I want to say f of b is equal to f of a plus the derivative of f at some point in between times b minus a. And the reason I wanted to do this is because this kind of looks like a Taylor series-ish. And so why do I say that? Well, you have the point where you're sort of centering your series around x equal to a. Then, the difference, that's your sort of x minus a term. And then you've got your sort of derivative in here as well. In particular, if I let x equal to b, then this looks maybe a little more familiar to you, except for that c term, right? That piece is maybe a little foreign in terms of the Taylor series. But here's what I'm going to say. This is like the Taylor series, and there is an abstract or a more general version of this, which is known as Taylor's theorem. So let's present that, and then we'll talk about it. So theorem. So again, this is called Taylor's theorem. So that is the same Taylor that all of these Taylor series are named after. And so we say if f and its first n derivatives, so that's like f prime, f double prime, all the way up to the nth derivative, are continuous on a closed interval I. So I stands for interval here, equal to, let's say, a to b. And the nth derivative is differentiable on the open interval a to b. So everything is it's continuous on the closed interval, and then the last derivative is differentiable on the open interval. These are more technical than you're probably going to need, but they become useful as you get into higher level and more advanced mathematics. Then there exists C between A and B. such that, and this is your sort of abstract or more general version of Taylor's theorem. So f of b is equal to f of a, okay, starting to look like the Taylor's theorem, times f prime of a. So this is just Taylor's theorem so far, right? I'm expanding this thing out. So f double prime of b, of a divided by 2 factorial. I'll keep the factorials in just so you can easily recognize this is Taylor's theorem with x equal to b, and then plus the nth derivative of a divided by n factorial b minus a to the n. So that is the Taylor polynomial expanded all the way up to the nth order, evaluated at b. That's all that I've written so far. So you might have to refresh yourself in the previous video, but then there's a remainder term. The n plus first derivative evaluated at c divided by n plus 1 factorial b minus a to the n plus 1. Okay, so this is what's known as Taylor's theorem, and the only difference between the Taylor approximation, the Taylor polynomial, and what's written on the board is this term right here, which we call the remainder. And what makes it different is that you have that c between a and b coming up in the derivative there. So that piece is allowed to be sort of tuned in order to make this thing equal. So let's just put some notes here. So note, if you write, b is equal to x, then essentially you've got f of x is equal to the Taylor polynomial. So let's write this. Taylor polynomial of degree n. And then plus what we'll term r sub n of x, which, as I just said, is the remainder term. So that's sort of how you can think of this. This remainder is telling you how much of a deviation you have as a function of x from your polynomial. Okay, so remember in the last video, I really tried to talk a lot about how you can approximate really complicated functions such as sine, which you probably don't think is being complicated, but it is, right? It is a genuinely complicated function because we need a Taylor series to describe it. And so what this is allowing us to do is capture how the function deviates from the Taylor series as we go up orders in the Taylor series. Now, this is sometimes called Taylor's formula. So what's written here, so from Taylor's theorem. And this remainder is, again, has the order n. Now, that's why we have the sub n here, but let's rearrange this again. Here's what I have. This tells me, I know that I didn't do anything. All I did was brought the Pn of x over to the left-hand side. But this is the interesting thing here, because this is exactly what I was saying. It's saying how different is my function than the polynomial approximation of it. And so that's really what the remainder is asking you, or telling you, sorry. It's really telling you, the difference between your polynomial approximation and your original function. Now, the other thing that we can say here is that, if the remainder goes to 0 as n goes to infinity for all x in I, we say the Taylor series converges for f, or 2f on I. Right? So this is exactly what I was talking about, right? This is what we were sort of using without properly defining in the previous video. And now we have a proper quantification of this based on Taylor's theorem. So if you bring it all back to where we started with the mean value theorem. The mean value theorem tells you essentially the error when you try to approximate a function by a constant, right? So if I try and approximate f of x by f of a, that's what's happening right here. You can think of the f of a term as the polynomial of 0 order, so p0 of x. Then this is r0, so maybe I can put that in there, r0 of x. This is p0 of x. And it's telling you, how much of a deviation you have in terms of x. Now, of course, this is going to be a bad approximation for almost any function. So what you want to do is you want to use higher order polynomials. And that's what Taylor lets you do. Okay, so let's do some examples. Let's take a look at how this works. Well, remember, we calculated the Taylor series for e to the x, right? So let's make sure that that thing actually converges for every single x. Because what we showed last week or last video, if you go back and you're very, very precise about what you saw, I said that the Taylor series centered at 0 is equal to, the Taylor series centered at 0 is equal to the function. And I said that the Taylor series always converges to some value. I never said that it converges to e to the x. That's what we're going to do here. Okay, so let's say show that the Taylor series generated by f of x equal to e to the x at x equal to 0 converges to f of x for every x in R. So for every number. And with this, that tells us that we can actually use the Taylor series to approximate the value of e to the x. You want to know what e to the 100 is? Use the Taylor series. You want to know what e to the minus pi is? Use the Taylor series. So how do we do this? Well, let's recall. So recall the Taylor series. So we have f of x is equal to the sum of x to the power of n over n factorial, where n runs from 0 to infinity. This is what we proved in the previous lecture where we expanded this thing out. And now this tells us that e to the x is equal to, let's say, 1 plus x squared over 2. We'll keep the factorial in there just so it looks consistent, plus ... x to the n over n factorial plus the remainder of x. And with the remainder taking the form of e to the c divided by n plus 1 factorial times x to the n plus 1. Now, where did the e to the c come from? Well, let's go back to our formula here. E to the c, well, e to the x, first of all, is the n plus first derivative. Every derivative is equal to e to the x here. Then I just plugged in the value c, and then I filled out the rest of the remainder term. And this is for some c between 0 and x, right? I centered at 0, I'm expanding at x. I want to show that this thing converges for every single x. Okay, so there's two cases. Let's do the first case first. So case 1, if x is less than 0, this implies that e to the x is less than 1, and also e to the c is less than or equal to 1 when c is between 0 and x. X and 0. And that just comes from the fact that e is an increasing function, right? So if c is between 0 and x, or sorry, between x and 0 when x is less than or equal to 0, then of course e to the c is less than or equal to 1. But this tells me that the absolute value of Rn of x is less than or equal to 1, which is the upper bound on e to the c divided by n plus 1 factorial times x to the n plus 1. Then the limit as n goes to infinity of 1 over n plus 1 factorial times x to the n plus 1, this thing goes to 0, as we showed in a previous lecture. And this works for every x less than or equal to 0. Okay, so that means that the Taylor series converges when x is less than or equal to 0. That's what that tells us, because by the squeeze theorem, we have that 0 is less than or equal to the limit as n goes to infinity of Rn of x, which is less than or equal to the limit as n goes to infinity of 1 over n plus 1 factorial absolute value of x to the n plus 1, which is equal to 0. So that means that we have convergence for every x less than or equal to 0. So case 2 now. X is bigger than 0. This implies that e to the c is less than or equal to e to the x for all x between 0, for all c between 0 and x. Why? Well, again, e is an increasing function. So if you're restricting yourself to between 0 and x, the biggest you could possibly be is x. And so e to the c is less than or equal to e to the x. But this now tells us that Rn of x is less than or equal to 1 over n plus 1 factorial. Sorry, it's not 1 anymore. It's e to the x over, or times x to the n plus 1. But now x is staying constant. You're letting n go to infinity. So do not let this confuse you, right? It might be a little confusing at first. But so then we can use the squeeze theorem again, and we could say that this limit again is equal to 0. So let's just write it out. E to the x over n plus 1 factorial, x to the n plus 1. You can, x is completely constant. Take that e to the x out, right? It's just a constant, whatever the value of x is. We're not changing it in the limit. And so this thing again goes to 0. So that tells you the remainder goes to 0 for all positive x as well. And therefore, that we have that e to the x is equal to the sum from n equal to 0 to infinity of x to the n over n factorial for every x in R. That's how you use Taylor's theorem in order to prove that a series is convergent. Now, there's another thing here that is kind of cool, right? So maybe you have seen how to obtain E. So some people, if you came from a business background, you'll see in compound interest, you can get E as the limit of this function right here. But there's another way to find E. And in fact, E is just equal to e to the power of 1, which is therefore equal to 1 to the power of n divided by n factorial, which gives us an infinite sum representation of E. So 1 over the inverse of each of the factorials, right? So this is 1 plus 1 plus 1 plus a half plus a sixth plus a 24th, and so on and so forth. And that is another equivalent representation of E that we can get from this. Okay, so there was an important piece in this example that we should all recognize, right? And essentially it came from bounding the nth derivative, right? Or the n plus first derivative in the remainder term, because if you look at what I did, I really just kind of used the squeeze theorem over and over and over again, right? And so that tells me that if I can bound the derivatives uniformly in n, then I can get convergence of the Taylor series. So this is called the remainder estimation theorem. So let's write this one down so we have it for our notes. So the remainder estimation theorem. So let's see what it says. So let's say if there is a positive constant, so m greater than 0, such that s dot t, the n plus first derivative at all values for all t between a and x, I should be careful because we don't know. So let's just say between a and x, because we don't know if a is, or if x is smaller than a or bigger than a. Then the remainder term Rn of x in Taylor's theorem satisfies the inequality absolute value of Rn of x is less than or equal to m and then x minus a to the n plus 1 divided by n plus 1 factorial. So this is just exactly what I did for the previous example. So we're just sort of writing this down so that you have it for your notes. You can use it whenever you want. Now, the other piece of this, is if this inequality holds for all n greater than or equal to 0, and the other conditions of Taylor's theorem are met, then the Taylor series converges to f of x. Again, all this theorem is really doing is picking out, what we already knew or what we did with the previous example. Okay, so it probably won't come as that much of a surprise, but again, it just sort of writes down explicitly everything that we were doing with that previous example. Okay, so how do you use this, right? So we've seen one example. Let's have a little bit more fun. Let's do another example. So let's say show that the Taylor series for f of x equal to sine of x converges, about x equal to 0. So at x equal to 0 converges for all real numbers. So in the previous lecture, we calculated what the Taylor series for cosine of x is. You can actually just follow that to find what the Taylor series for sine of x is as well. I believe I gave it to you, but let's just write it down. So note f of x is equal to the series, and in this case, we're going to state it in terms of k's because this has only odd components. So we get -1 to the k, x to the 2k plus 1 divided by 2k plus 1 factorial. Now, if you remember what the cosine series was, it was -1 to the k, x to the 2k, it was only even terms, divided by 2k factorial. Sine is an odd function. It only has odd elements in its Taylor series. And so essentially what this tells you is that, so sine of x, if we expand this out using Taylor's theorem, this is x minus x cubed over 3 factorial plus x to the 5 over 5 factorial minus, and then so on and so forth. Let's go up to the general term. Let's imagine that we quit at some k. So this is the Taylor polynomial of order 2k plus 1. So this is p 2k plus 1 of x, just like we saw with the cosine function last time. Every second Taylor polynomial is exactly the same. So what I did is I just looked at the odd ones because these are the ones that really matter. And then the remainder here of 2k plus 1 of x, and with the remainder of 2k plus 1 of x equal to, now this is going to be the 2k plus first derivative evaluated at some c divided by 2k plus 2 factorial. Sorry, this should be 2k plus 2 up in the number of derivatives, and then x, sorry, it's x minus 0, so I don't need brackets on this, x to the 2k plus 2. Okay, so what am I going to do? Well, I know that every derivative of sine is plus or minus sine or plus or minus cosine. In fact, the even derivatives are just cosines, plus or minus cosines. Sorry, the even derivatives are plus or minus sines. I apologize for that. But the point is that we have that the absolute value of these things, these are less than or equal to 1 for every k greater than or equal to 0 and real number c. So this implies that my remainder terms are less than or equal to 1 over 2k plus 2 factorial, and then x to the 2k plus 2. And so from the Taylor remainder theorem, or sorry, from the remainder estimation theorem here, we know that the Taylor series is going to converge everywhere because we're able to bound this remainder term, or the derivative in the main remainder term, regardless of the value of c and x. So it works for everything. Therefore, this Taylor series converges everywhere. And if you want to, you can go back and you can do the same thing for cosine as well, right? Why? Because the cosine remainders are just written in terms of derivatives of cosine, and derivatives of cosine are sines and cosines again, up to pluses or minuses. And so again, it's between -1 and 1. So this is fascinating, right? Let's just summarize what we've seen so far. We've seen that the Taylor series of e to the x, sine of x, and you can get that the cosine of x series, they converge for every single x and r. And so this is what I was trying to emphasize with the previous video. You saw that you can take, you can find sine of 10, for example. You just need to put it into the Taylor series. And then you expand that Taylor series up until you watch for convergence, right? And I'm going to do an example in a few minutes here that's going to make it explicit how we can figure out, how many terms the Taylor series needs in order to get error within a certain order. This should feel familiar because it's very, very similar to what we do for the trapezoidal rule, for Simpson's rule, for estimating these integrals. It's a very, very similar process. And again, it should be similar because it's just using summations, right? You're just asking how many terms do I need to add together before this thing gets really close to where I want it to be. Now, before I do that, let's use some Taylor series to come up with Taylor series of other functions. This is the real beauty of this, is that now I've got some base functions like sine, cosine, e to the x, blah, blah, blah. Now I can use this to come up with Taylor series for other functions without having to calculate derivatives. So let's call this maybe using Taylor series, the practical aspect of it. So example, let's say 1. Let's find the Taylor series. So find the first few terms. Of the series. Taylor series of f of x equal to 1/3 and then 2x plus x cos x about x equal to 0. Okay, well, here's the thing. We already know the Taylor series for cosine of x. So let's use that knowledge in order to find out, the first few terms of this thing. Actually, we can write it explicitly, but we'll do the first few terms. First thing I want to do, I want to expand that 1/3 into the brackets. So I get 2/3 x, and then I get plus x over 3 cos of x. And now let's write out the first few terms of cos of x, and we can multiply an x over 3 into them. So remember, cos is 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial minus, and then all the way up, in general, just so that you remember this, the general term of these even powers on x's. And then this is an infinite sum. It keeps going, right? We're not asking for the approximation. We're not asking for the polynomial. We're asking for the specific Taylor series. And let's expand on a few terms here. Let's take a look at what we can get. 2 over 3x plus, now let's distribute my x over 3 into every single term here. And I can do that. This is just sort of standard distributive arithmetic. So I get x over 3 minus x cubed over 3 times 2 factorial plus x to the 5 over 3 times 4 factorial. And let's just let that keep going out from there. I'm going to only go up to that fifth order. Okay. Now I have 2/3 x plus 1/3 x. That gives me a nice x at the front. Then minus x cubed over, and this is going to be 3 times 2 factorial. That's going to be 6. And then plus x to the 5 over 3 times 4 factorial. You might have to use a calculator for that, but it's 72. And there it is, right? This is the first at least 3 terms of this Taylor series. Now, the one thing that's worth absorbing here is that your Taylor series for cosine only contains even powers. So that means that the Taylor series for x times cosine, or x over 3 times cosine, only contains odd powers. Similarly, if you add 2x over 3 to that, you again have only odd powers. So from what I talked about last time, you have an odd function here, right? Because it only contains odd powers in its Taylor series. So that's kind of a cool thing, right? Okay, let's do another one. Maybe you're not that impressed. Let's try, so same problem for let's do, this one is going to be hectic. It's going to be ugly. E to the x cos of x. Now, think about if you had to do this, this Taylor series sort of by hand, there's a lot of derivatives and they're going to get ugly fast, right? The first derivative is a product rule already. And then after that, it just gets worse and worse and worse. So we can use our known expansions for these things and get some nice results, at least for the lower order terms, the terms with lower polynomial degrees. So let's remind ourselves of what e to the x is. So the series for e to the x is 1 plus x plus x squared over 2 factorial plus x cubed over 3 factorial. And then, well, we'll go up to the fourth order, x to the 4 over 4 factorial, and so on and so forth. And cosine, we just did it, 1 over x squared over 2 factorial plus x to the 4 over 4 factorial minus x to the 6 over 6 factorial. And we can let that one keep running up. I'm actually only going to calculate up to degree 4 here, just for the sake of this, because it gets quite tedious as you go on. But let's see how this works. We've sort of seen something like this already. I'm going to take this 1 and multiply it into everything in the brackets. Then I'm going to take this x and multiply it everything into the brackets. Then x squared into everything in the brackets. So I'm going to get an infinite sum of infinite sums. Okay, so it's going to be ugly. Let's take a look. The 1 multiplied by everything in the cosine bracket just gives me cosine back. So let me do this. And let's stop that thing at this order here. Okay, so that's multiplying 1 into everything in those brackets. Then let's do the same thing for multiplying x into everything in those brackets. So plus, now I'm taking x, which is the second term, into the e to the x expansion, and multiply it into everything in the cosine expansion. X minus x cubed over 2 factorial plus x to the 5 over 5 factorial. Now the next one is going to be x to the 7. I'm only going to do this expansion up to x to the 4. So it's okay. I'm going to quit at x to the 5 here. Okay, let's do another one. X squared over 2 factorial gets multiplied into every single term in the cosine bracket. X squared over 2 factorial minus x to the 4 over 2 times, 2 factorial times 2 factorial. And then everything is bigger than the 4th power, so I'm not really interested in it right now. And then let's do another one. I can multiply in the x cubed over 3 here. So I get x cubed over 3 factorial minus x to the 5 over 2 factorial times 3 factorial, blah, blah, blah. Everything after that is too big. Again, I just want to expand up to the 4th order. So one more term, I'm going to take that x to the 4 over 4 factorial, multiply it into my cosine series, and that's going to give me my last 4th order polynomial degree term. So I get x to the 4 over 4 factorial minus x to the 6 over 4 factorial times 6 factorial, blah, blah, blah. And then plus dot, dot, dot. Now here's the issue. Here's the thing. I decided that I wanted to go up to polynomial degree 4. I want to find the first 4 terms of this, or 5 terms of this. Okay, that's wonderful, but it comes with an issue, right? You have to be very, very careful that you're not going to miss any terms. So you can see I have a lot of brackets being expanded up here. And that's because I was very careful to make sure that I'm not going to miss any 4th order terms when I do this multiplication. Because if I take the x to the 5 over 5 factorial, which would be the next step, then that is going to give me at least a degree 5 term coming from this multiplication here. So that means that I can ignore it. Okay, so we have to be very, very careful. Now, if you start collecting terms, there is only one degree 0 term, and that comes from right here. Then the degree 1 terms, again, there is only one of them coming from right here. Then the degree 2 terms, there's a minus x squared over 2 factorial, and there's a plus x squared over 2 factorial. They add to 0, so there is no x squared terms here. Then the cubic terms, you have x cubed over 2 factorial, minus x cubed over 2 factorial, and a plus x cubed over 3 factorial. And in this case, you can find that this is going to give you, after you do a little bit of adding and subtracting here, you get x cubed over 3. And then the final term, you can do the same thing with the 4th order terms. You can see that this is getting hectic. You've got 1 here, you've got 1 here, you've got 1 here. So when you put all of those together, you're going to get x to the 4 over 6, and so on and so forth. So as you can see, it makes sense why I stopped at degree 4, because things are going to get really, really complicated. The degree 5 terms, there's going to be even more of them that I have to be careful of here. So I stopped at degree 4 because this thing, it doesn't seem to have that much of a pattern where I can just figure this out. Okay, so now let's see how we can use this in another way. Let's do a simple problem of, let's say, find the Taylor series of cos of 2x about x equal to 0. Well, in this case, we can use one of our theorems or one of our results from power series. This is a composition. So cos of 2x is equal to the sum n equals 0 to infinity minus 1 to the n. You can use a k in here. Actually, I will use a k just to keep things consistent. K equal to 0 minus 1 to the k, and the power is going to be 2k, and you're going to get 2k factorial. But now you're replacing all x's with a 2x. It's just a composition of functions. And so this is going to give me the sum from k equal to 0 to infinity of minus 1 to the k, 2 to the 2k times x to the 2k divided by 2k factorial. Sorry, the factorial goes on the outside. And if you want to, there's one last simplification you can do. Let's say this is the sum from k equal to 0 to infinity, minus 1 to the k, 2 to the 2k is the same as 4 to the k, x to the 2k divided by 2k factorial. That was 1, 2, 3 steps instead of having to find a bunch of derivatives. Okay, so let's do one more example, and this is more computational in nature. This is how you would use a Taylor series and a Taylor polynomial and the remainder theorem in order to approximate the value of a function at a certain value of x using its Taylor series. So let's consider the following. So for what values of x can we replace sine of x by, so it's first expansion, or sorry, it's a third order expansion, x cubed over 3 prime, so a cubic polynomial, and obtain an error whose magnitude is no greater than 3 times 10 to the minus 4. So what you're doing here is you're specifying what the error that you're willing to tolerate is. And then you're asking yourself, okay, if I want to approximate sine by x minus x cubed over 3 factorial, what are the values of x that I'm able to do that for, right? What is the values of x where the sine function and this truncation, this Taylor polynomial, are within 10 to the minus 4, 3 times 10 to the minus 4. Okay, well, this tells us, so from Taylor's theorem, we have that sine of x minus x minus x cubed over 3 factorial. Well, this thing is equal to, so we're going to go up to the next term in this series. This is x to the 5 over 5 factorial minus x to the 7 over 7 factorial plus x to the 9 over 9 factorial. So all I did is I wrote out the series for sine and I took over the first 2 terms that I care about. So that tells us that after x cubed over 3 factorial, we have, or we are no greater, or the series is no greater. We are no greater than x to the 5 over 5 factorial, which we can slap absolute values around this thing because we want to know the difference between the left-hand side, which is putting an absolute value here, which is putting an absolute value here. And so Taylor's remainder theorem, we have x to the 5 over 5 factorial. This is less than or equal to x to the power of 5. And then 5 factorial is 120. This is the remainder. So this is the Taylor remainder, if you want to call it that. And so we essentially want to know what the values of x's are so that this is smaller than 3 times 10 to the minus 4. Now you can multiply up the 120 and you can take a 5th root, and this tells you the absolute value of x is smaller than 360 times 10 to the minus 4. And then all under the 5th root to try and get x back, which is about 0.514. So therefore, minus 0.514 is less than x, which is less than 0.514. That gives you the range of x values for which you can replace the sine function by x minus x cubed over 3 and guarantee that those 2 functions are within 3 times 10 to the minus 4 of each other. Now you can imagine repeating this, right? You could imagine saying, okay, I want to approximate sine up to 10 decimal places. You know, how do I guarantee that my little cubic approximation of sine, x minus x cubed over 3 factorial, what are the values of x that I can guarantee that's within 10 decimal places, right? It's a common thing that you hear sometimes, a little joke that engineers will replace sine of x by x when x is very small. Well, what they're doing is they're using a Taylor approximation, right? They're just using the first term in the Taylor series in order to approximate sine of x when x is really small. And now what you can do is you have the tools using Taylor's theorem and this precise remainder to determine how good of an approximation that is based on what the error you're willing to tolerate is. If you were only willing to tolerate, being off by about 2 decimals, so 10 to the minus 2 error or so, 10 to the minus 3 maybe, then you might be able to allow larger x values. But if you want to be super, super precise and allow an error of maybe you want all 10 decimal places to be right, so 10 to the minus 11 for your error, then the values of x's where sine of x is approximated by x is very, very small based on your error tolerance.